Bioinformatics Micromodules, Maximum Parsimony for Phylogenetic Tree Reconstruction, Part 2. In this module, we analyze Feature's algorithm for solving the small parsimony problem and study an extended version of the algorithm that finds all solutions to the small parsimony problem. In the last module, we studied Feature's algorithm that involves an upward phase for gathering preferences and a downward phase for making decisions. To prove that the solution identified by the algorithm is optimal, we can use induction. First, in the base case, if there are only two leaf nodes, there are only two possibilities. If the two leaf nodes have the same nucleotide, obviously the optimal solution is to assign the same nucleotide to the root, leading to no mutations along all the tree branches. Feature's algorithm does exactly this. On the other hand, if the two leaf nodes have different nucleotides, obviously the optimal solution is to assign one of them to the root node, leading to one mutation along the tree branches. Feature's algorithm also produces such a solution. Therefore, for this base case with two leaf nodes, Feature's algorithm is optimal. Now, assume that Feature's algorithm is optimal for any trees with k or fewer leaves. Then for a tree with k plus 1 leaves, the root has two children that we call L and R, each of which has no more than k leaves. Suppose also that if they were the roots, the optimal solutions would have ML and MR mutations respectively. Now, if we run Feature's algorithm, in the upward phase, we will obtain preference sets SL and SR for these two nodes. As usual, there are two possibilities. The first possibility is that SL and SR have some nucleotides in common, in which case the root would keep these common nucleotides as its own preferences and select one of them in the downward phase. This forces L and R to choose also this nucleotide in the downward phase, and no mutations are introduced along the branches that connect the root to these two nodes. Is this solution optimal? Since the nucleotide that L is forced to choose is also in its preference set, the resulting solution for the left subtree is also one that can be formed by Feature's algorithm. By the induction assumption, the number of mutations in the left subtree is exactly the optimal number ML. In the same way, the number of mutations in the right subtree is exactly the optimal number MR. The total number of mutations in the whole tree is therefore ML plus MR, which is optimal, since it is impossible to have a solution with fewer mutations. In the second possibility, the preference sets of L and R do not have nucleotides in common. In this case, Feature's algorithm would take their union as the preferences of the root, and then select one of them as the root's decision. Without loss of generality, suppose the root chooses a nucleotide from L's preference set as its own choice. Then the discussion for the left subtree is exactly the same as the first case. For the right subtree, since the root chooses something not in R's preference set, according to the algorithm, it would simply ignore the root's choice and select one nucleotide from its own preference set. The total number of mutations in the whole tree would then be ML plus MR plus 1. Is this optimal or not? If Feature's algorithm has not missed any optimal solution with a different nucleotide at the root, then this solution is optimal, since one extra mutation has to be introduced between L and R. This is indeed the case, although we will not prove it formally here. Instead of going deeper into the proof, let's discuss an extended version of Feature's algorithm that can find all optimal solutions. This extended algorithm is very similar to the original algorithm, with also an upward phase and a downward phase. The upward phase is identical to the original algorithm. The only difference is in the downward phase, that each non-root internal node performs a majority vote among the actual choice of its parent, the preference set of the left child, and the preference set of the right child. Now, let's revisit our previous example with this extended algorithm. The upward phase is the same as before. In the downward phase, the extended algorithm gives 3 solutions instead of 2. The first 2 solutions were also identified by the original algorithm. The third solution chooses A for the circled node. For this node, the parent has chosen A, the left child prefers G, and the right child prefers T. Therefore, by the majority vote, A, G, and T all have 1 vote, and each of them forms an optimal solution. Let's look at a slightly more complex example with 6 leaf nodes. In the upward phase, we gather the preferences upward. For the parent of the leaf nodes having A and C, it keeps both. For the parent of the leaf nodes having A and A, it has to choose A. Each parent then has to keep both A and G. The parent of it in turn has A and G on one side and G on the other side, and thus keeps the common nucleotide G as its preference. Finally, the root has A and C on one side and G on the other side, and therefore keeps all of them as its own preferences. Then in the downward phase, the extended algorithm produces 6 solutions in total. First, suppose the root chooses A as its choice. The left node now has 2 votes for A from the parent and the left child, and 1 vote for C from the right child, and has to choose A. The right child of the root has 2 votes for A from the parent and the left child, and 2 votes for G from the left child and the right child. It can thus choose either A or G. Suppose it chooses A. Then, using the same method, each child node has to choose A. Finally, the remaining internal node also has to choose A, which completes the first optimal solution. To find out other optimal solutions, we trace back our decisions. Suppose again that the root chooses A. The left child still has to choose A. This time for the right child, let's choose G instead. The child of it has now 1 vote for A and 2 votes for G, and has to choose G instead. Finally, the last internal node still chooses A, since there are 2 votes for it. We can then continue with other choices of the root and the internal nodes. Finally, after enumerating all possible choices allowed, we get 6 optimal solutions. Before ending, let's go back to the issue of having multiple sites. If we assume the input sequences are all aligned and the different sites are independent, what we need to do is simply running the algorithm for each site one by one, and then considering all their combinations. For example, consider a tree with 3 leaf nodes, each with 2 nucleotides. In the upward phase, we collect preferences for each site separately. For the left child of the root node, at the first site, it keeps both A and G from its children, while at the second site, it keeps the common C from its children. The root then keeps the common G for the first site and both C and T for the second site as its preferences. Then in the downward phase, the root has to pick G for the first site and C or T for the second site, which forms 2 separate sets of solutions. If the root picks C for the second site for its left child, the first site must be G since it has 2 volts, and the second site must be C since it has 3 volts. If the root picks T at the second site, it happens that its left child still picks the same nucleotides at the 2 sites based on the majority vote rule. In summary, there are 2 solutions, each of which involves 1 mutation at site 1 and 1 mutation at site 2. We have finished our discussion on the small parsimony problem. Recall that in the more difficult large parsimony problem, the tree topology is also not given. In that case, the strategy is to select some tree topologies to start with, run the algorithm for small parsimony to find their optimal solutions, and then use the results to look for other promising tree topologies to test. This is a typical searching problem setting in artificial intelligence. Many methods have already been proposed to avoid issues such as trapping at the local optimum during the searching process.